All right, so last week we were looking at how do we build graphs in Google Sheets. We also looked at how we use y equals mx plus b to calculate things that may or may not be on a graph. Right? What we're going to do today is we're actually going to get some real data ourselves. We're going to plot those graphs, and we're going to look at what we can get from a position versus time graph, because that's the type of graph we're going to be building. Okay? Tomorrow, I'm going to go over in detail how a position versus time graph works. I just couldn't get the Chromebooks for tomorrow, so I had to kind of shift my lessons a little bit. Okay? So I'm going to teach you about position versus time graphs tomorrow, but we're going to actually do the lab when we get the data and assemble them today. You can do most of this lab without really knowing kind of how a position time graph works. Okay? So we'll kind of walk through that, because we already know how to use y equals mx plus b, and that's the bulk of doing this. So what we're looking for here is what's the relationship between distance or position and time for an object that travels at a constant speed. Okay, so I want you to think about what that would look like. If I had an object traveling at a constant speed, okay, and I had a graph that had its position okay, so if I have position and time, and the object's traveling at a constant speed, what is that graph going to look like? It's going to look like a straight line. Not horizontal though, right? Okay? It's going to look like a straight line going up. Now, the points are never going to be perfectly in a line, but I mean, it's generally going to have that pattern. Okay? Now, why does it have that pattern? It's going at a constant speed. What does it do every second? Move what? The same amount. Okay? That's what we have to understand about an object traveling at a constant speed if we want to know the relationship between position and time. Okay? The relationship between position and time, spoiler alert, this might be important later, okay, is linear for an object traveling at a constant speed. It's linear because every second the object goes the same distance. Okay? That's what it means to go a constant speed, to travel the same distance every time interval. Everybody okay with that idea? Okay? There are different kinds of relationships, okay, on a graph. This is a linear relationship, okay, or a positive linear relationship. Okay? A graph that looks like this is still linear, but it's negative or inverse. Okay? It means that as time goes up, position goes down, or becomes more negative. So this would be an object moving forwards. This would be an object moving backwards. Okay? This would be an object not moving. Okay? Because its position isn't changing. Right? Now let's throw something a little different. What's that object doing? It's accelerating. Good. Most of the time people don't guess that. Okay? This object's accelerating. If you're accelerating, you're going faster and faster. That's why this line curves. If you go faster, is the distance you travel every second the same anymore? Okay? And so this is showing that, let's say in this time interval, okay, from here to here, the object only went this far. Okay? But in that next equal time interval, it went a lot further. Okay? And if I do that again over here, see how much bigger those vertical parts are getting? Because it's going farther every second. Okay? It's going faster every second. Okay? But we're going to be dealing with an object traveling at a constant speed, so the relationship will be linear. All right. So, your hypothesis, we'll need to talk about that because it says generate a hypothesis about the relationship between distance and time for an object traveling at a constant speed. So here's what I want. Okay, in the if part, talk about that relationship. Oh wait, I might have spoiled that already. Okay. Okay, the and part, we describe the experiment. I haven't gone over that yet, but it's pretty simple. Okay. In the then part, you need to tell me how you can calculate speed of the object, and this is the key part, using only your graph, your position versus time graph. Now, we built one of these last week and found out how we can actually calculate the speed of an object or the velocity of an object from a position versus time graph. Okay? We'll go over that in a little more detail later. That's what needs to be in the hypothesis. Okay? The key part is this. Okay? In other words, I do not want anybody just doing this. Okay? I do not want you calculating speed using d over t. That would be the last point you have, the last data point you have in your chart. Okay? Divided by the biggest time you have in the chart. You don't need to build a graph if that's the way you're going to do it. Everybody follow? All right, for our design, our variables. Okay? In this graph, the two things that are going to be on the graph, or in this lab, sorry, the two things that are going to be in this graph are time and position. We talked about last week, which one goes on the x-axis and which one goes on the y-axis. In terms of manipulating, it always goes on the x. Responding always goes on that. Okay, wow, that's some free marks right there. Okay, now, a lot of people have trouble with this because they look at time and they go, there, you can't travel through time. Therefore, you can't manipulate time. Yes, you can. I'm not going to manipulate how time travels. I'm not going to manipulate what direction I travel in time. But I am setting kind of an upper limit on how long I'm going to let the experiment run for. By doing that, I am manipulating time. By choosing the period of time over which the experiment will run, I will effectively determine how far the object can travel. Okay? So even though I'm not technically manipulating time, okay, I am still determining how long the experiment runs for, and that is a manipulation. Okay? If I allowed the experiment to run a shorter length of time, the cart wouldn't go as far, okay, and vice versa. All right, so we have our explanation and identification for our variable there. Okay, you guys can do that responding. How many controlled variables do you need? 3. All explained. Okay, now, here's how this lab's going to work, so you can start thinking about the controlled variables. We're going to take these 5 carts that I handed out. We're going to go to the atrium. Okay, we're going to put measuring tape on the floor. Okay. We're going to allow each cart to run along this tape for, I think, 40 seconds. 30 or 40 seconds. We'll decide. Okay? Each cart will travel along the tape, which means kind of the same place. Okay? When we're out there and the lab is running, I think you'll be able to come up with a couple more control variables. So, when the cart is running, this is how that's going to look. Okay, we're going to have one person who's responsible for timing. That is, make you in charge of timing. Okay, you just need to use the stopwatch. Okay, and I'm going to have one person who is going to measure and mark the location of the cart every 5 seconds using these little yellow sticky notes. Right? So the carts will run because Elise will say go, and the person with the cart will set the cart down and it'll start running along the tape. Okay? Every 5 seconds, Elise is going to tell Seamus to put a yellow sticky note on the tape where the cart is located. Okay? I would suggest always marking where you think the front of the cart is located for consistency. They don't go to the okay. They also, unfortunately, don't go very straight. And that isn't the fault of the carts, it's the fault of the floor. Okay? I don't know if you guys have noticed this, but they've actually fixed the floor probably 5 times since we came into this building. Okay, the first time we came into this building, the floor in the atrium looked like this. I kid you not. Okay, it was like the guy on the power trowel was drunk. Okay, that's what it looked like. It looked like someone had taken a freeze frame of an ocean during a storm. Okay, bubbles everywhere. So the carts going like this, and they still do. Okay, a little bit, even though we've resurfaced that floor a few times since we've been in here. Okay, it's still not perfectly flat. And of course, the carts aren't perfect either. So the person who is responsible for each cart will need to keep the cart on track. And you will do that by gently nudging the cart with your foot. Nudging. Okay? So that'll look kind of like this. If I want this cart to travel in a straight line, I will start it and set it on the floor, and then I will walk above it, gently nudging it into a straight line as it goes along. Okay? Just gentle nudges with my foot to keep it going straight. Okay? It's a pretty simple technique. The foot does not need to swing backwards. Okay? It just needs to nudge the cart. Okay? So, what you're going to want to do to help Seamus out is try and keep that cart right beside the tape. Okay? That way he can mark as best he can the location of the cart using the sticky notes. Right? When each cart is done its run, I will read out the distances. Okay? And I will do that by reading where the front of the sticky note is on each sticky note. Okay? On the tape. I'll read out where it is on the tape each time. And you guys will have the Chromebooks out there and you will enter the numbers. Okay? Everybody following me. That's why you incidentally have a spreadsheet that goes along with the assignment. And if you go into the assignment here, okay, you'll have a graphing lab report and a graphing lab spreadsheet, okay, in Google Classroom. So most of you will be working out of this one, okay, to start with. And we're going to do 5 carts. All right. Okay, so we'll have all of our data, okay, and then you'll have these analysis questions. So, first off, show how you would calculate the slope of each car's line on the graph. That means I want you to manipulate y equals mx plus b for slope. So that means you have to remember what part of this equation represents the slope of the line and show me that equation manipulated for it. Okay, so just move things around. Okay, question number 2. Using the equations for each car, okay, and that Google Sheets will spit that out, right? It spits out y equals mx plus b for each line. Okay, using the equations for each car, calculate how far each car would travel in 150 seconds. So, again, using y equals mx plus b to solve for how far they would travel in 150 seconds. Okay, and third question, using the equations for each car, calculate how long it would take each car to travel 100 meters. Okay, and again, show your work. So my suggestions for that would be that you can try and type in your calculations. That can work. It's nothing terribly complex. Or you can write them out on paper, snap a picture of them, and insert the picture into the lab report, whichever way works for you. Okay? But I need to see your calculations. All right, same as always, conclusion, copy paste your hypothesis, and then explain, was the relationship linear? Okay, did all the cars produce roughly linear lines, okay, or graphs, things like that. Okay, and then 2 sources of error and ways to fix them. There's kind of a big one that I demonstrated earlier. All right, and obviously you don't have to do the class discussion questions. We'll talk about those after I hand back on November 7th. Okay, we're due on the 25th. I won't be here on the 26th to go over them. I'll go over them on the 27th. Okay, big enough physics kids to listen. So we go and we ride all the rides. We'll stay here. Have fun. All right. Any questions on what we're doing? So here's the thing, guys. We are going to be in the atrium. And there are classrooms near the atrium. So we need to be mindful of how much noise we make on our way there and while we're in there. There are going to be a lot of people with nothing to do, okay, until I start reading out the measurements. Okay? try to keep noise to a minimum so we're not disrupting any classes. Right? Okay. In your lab report, under procedure, it says copy and paste your Google Sheets table and graph here. So this is what I want you to do. Okay, you've got your data here. Highlight it all. Copy it. Okay, so like Control C. Right, copy it over. Come back to your lab report and put it here. Okay, so Control V. All right, and it's going to ask you, do you want to link it to the spreadsheet? You do, because if you find that you have to change something, any changes you make in Google Sheets will automatically show up in its copy in your lab report. Saves you having to do it twice. Okay, so I click paste here, there's my chart. Okay, I want to do the same thing with my graph right underneath. So I go to my graph, I click on it, the little dots, the 3 dots over here, okay, copy chart. Bring it over to my lab report. And I do want to link it as well. Then I've got them both there. Okay, you have the graph built, get it in there, okay, and then get going on the analysis. You've got quite a bit of time here. It's not like the analysis is terribly complex. We did a bunch of that stuff last week. All right, I got the rest of the class to work on it.